Welcome for this session of masterclasses. Today we have the pleasure to listen to Josué Tchouanti from Institute of Mathematics in Toulouse. And he'll give an introduction to birth-death processes. Josué, please.
Thank you very much, and thank you for the invitation. It is a great pleasure for me to be here. I am an associate professor in Institut Mathématique de Toulouse. My work focuses on studying stochastic processes with application in biology. And I'm mainly working on population processes, population dynamics, and also evolutionary dynamics, which means the way some species are able to develop adaptation for the environments, in fact. Since there are a lot of features in the environment that can impact their behavior. So this is what I'm studying. So for this session, for this masterclass, I made the choice to talk about something which is very simple. It is a population, a sort of model of population dynamics, but which is very, very simple. It is the basic type of population process. You will see it is very simple. It is what is called the birth-death process. The session we will have will be subdivided in 3 parts. The first one will be on the definition of what is birth-death process, what are some very simple properties that we can get from the definition, how do we represent it, for example. This is the type of things that we will do in this first part. In the second part, we will look at a bit technical, but not so much, property, which is the long-time behavior of the birth-death process. Do we have explosion? Do we have extinction of the population? Do we have a stationary regime that can emerge? This is the type of things that we will discuss about. And in the third part, if we have enough time, we will just we will see, not really enter into details, but we will see some extensions, some stuff that we can do that are harder than just studying the long-time behavior, but looking at what we call the scaling limits. So how do these process, or the family of those processes, behave when we have some scaling parameters that can go to a certain critical limit, for example, the size of the population. So, about the first part, I will give a very simple definition of what we call a birth-death process. For those of you that are familiar with probability, you know that a large part of probability is focusing on studying random variables. What we call a stochastic process is just a random variable, but whose values are in a set of functions of time. So you can see it just like this, okay? So what we will call a stochastic process will always be denoted as something like this. A family of random variables depending on time, or you can also see it, as I said, as a random variable with values in a set of functions. For example, the set of continuous functions, we can consider that you have a continuous stochastic process, and that's it. So, it was just a word about what is called a stochastic process, and I will give the definition of what we call a birth-death process. So, the birth-death, I will always denote BD, so it is for birth-death. A BD process is an n-valued stochastic process So it is stochastic, it is Markovian. I will give an explanation of this word. It is a pure jump process characterized by the transitions first I write it and I will explain. So, I told you what is a stochastic process. A Markovian process is a particular type of stochastic process whose future is completely determined by the present of the process. It doesn't look at the whole history of the process. Okay? So, this is what is called a Markovian process. And what we call a pure jump process, it is a stochastic process that only jump. There is no continuous behavior between, we just have jump. Like you can think about the counting process. Okay? So just to get an idea of what it is, you can assume that you are working on the campus of this university, and when you meet a new student, you just increment a quantity. So you will have a pure jump process. Okay? So the birth-death process is a specific type of process with all those characteristics that only jump from a current value to this value plus 1 or minus 1. It is the only two possibilities. And when we describe the transitions of a stochastic process, which is a pure jump process, we need to define what are the destinations when we have a jump, but also what are the rates of those jumps. The rate is a sort of, a sort of clock that tells you at which frequency or at which speed you will have the occurrence of this mechanism. Okay? So, we define here the rate of this one as lambda n. It is always positive or non-negative. And for this one, we will call it mu n. So here, this mechanism corresponds to birth. So we will say that this thing is the birth rate. And this one corresponds to death, and you will say that this rate is the death rate. So why do we consider that this mechanism can be called birth? Because in fact we have it is just like we have a new individual in the population. Okay? You can consider that you have an asexual population and there is one individual in those that were present in this family that gave birth to a new one. This is the idea. So this model is very simple, and it has a lot of applications in biology. So it is a way we model populations dynamics, because in a population you always have just birth or death. Sometimes immigration, but an immigration is also can also be seen as a birth mechanism, since you have an increment, like you have one individual that can be added in the population. But the family of birth-death processes can be seen as a bit more general than this, but we'll only focus on the types, on those types where we have +1 or -1. So another example which is very interesting is the Q models that consist on a very simple thing. You assume that you are in Upsidum waiting for your waiting in a queue to get to pay your food. And then the number of individuals in the queue can be seen as a birth-death process. Since you have some that pay their food and then leave the queue, and you have new people that got their food and joined the queue. Okay, so you have a -1 because a person paid, and you have +1 because a new individual arrived. And the different type of question you can ask yourself, arriving, for example, in Epsilon, is like the size of the queue. Will it end at a moment or not, for example? So maybe the people from the that got the payment will stay there for the entire day, I don't know. But it is a type of question you can ask with those kind of models, for example. So I will give here a sort of formal definition of this with probabilities, because this is the Markovian representation, but I also want to give you a sort of intuitive representation of what we mean when we write this. The idea is the following. If we have a very small time delay, which is positive and small, then first property, the probability that we move from the value n at time t to a value n+1 at time t plus h. So it is a probability of having the value n+1 at time t plus h, knowing that the value of the process at time t is equal to n. This quantity has the form. Okay, so this is a birth mechanism. So it will have the form lambda n h plus something which is smaller than h. This is the idea. So this probability is totally controlled by the birth rate. Same for the death rate, where here, if we assume that we have a current state that is n at time t, and we want to determine what we will have at like a small moment just after t, the probability that we get n-1 is equal to mu n h plus something smaller than h. And the third property is that either we have this, or the process doesn't move. Okay? And in this case, we'll have this one, knowing xt equal to n. This will be 1 minus the sum, this one and this one, plus this h plus something that is smaller than h. And if we have something else here, it will be just something smaller than h. The idea is that the main mechanism that will happen when you will consider very small delay will be either a birth mechanism here, because you move from a position where the process was n to a position to the value n+1, either this one or this one, where you move from n to n-1. And what we say here is that if we do not have one of those two, then we most likely have this, most likely the stochastic process doesn't move. Okay? And this is what we have here, and this is also why the probability we have here is 1 minus the dominant part in those two probabilities, the sum of them. And we always have a rest. So this is a very formal representation, but that can give some intuitions on how to understand the way this stochastic process behaves. May I clean the blackboard? So before cleaning the blackboard, I will show you an example of this. This is an example of trajectory of the birth-death process, where you will see this red curve, which is like it is exactly xt. It will jump from its current position, for example, here, to +1, and there is a moment somewhere, like there is a moment here where it jump of -1, and it is just like this: +1, -1, +1, +1, +1, -1, and etc. We choose some particular specific values of lambda n here, and mu n also here. You have to make sure with those processes that mu0 is always equal to 0. Otherwise, you will have a negative amount of individuals. It is not realistic to have this kind of values. So how do we construct this? The idea is always the same. You have a current moment. You want to construct a future moment and understand what happened at this moment. And for that, maybe I will clean here.
Sure.
Yeah?
Can you repeat what you said about the mu n so that it's not negative?
If mu n is non-negative, is positive when n is equal to 0, then when your population will be at 0, there will be a possibility to have to reach the value -1. But when mu0 is equal to 0, this means that the rate is 0, so the mechanism will never occur. Okay? So how do we construct this? You have a current moment that I call tk, where the process has the value, this is the times, where the process has the value n. Let's say here we have n minus 1 and n plus 1. So the first step consists of simulating an exponential distribution here, an exponential distribution with a parameter lambda n plus mu n. N is exactly the value of the population size. When we do that, we obtain this new time, which is k plus 1. And we want to know, like, we have this thing because in those intervals, the population remains constant. It is a pure jump process. The jump can only occur here. So we have this, that is, the point is rejected, and we want to understand what happened at this moment. In order to understand this, the idea is the following. With probability lambda n over lambda n plus mu n, it will be a birth. And with probability mu n over lambda n plus mu n, it will be a death. So when you reach this moment, you just throw a piece of money and you see, okay, I have birth with this probability and death with this probability, and it is very easy to do that on a computer. You just have to simulate a variable according to a uniform distribution and make some comparison. It is very easy. And then you determine by this process which mechanism you have here. If it is a birth, then the process will go from n to n plus 1, and it will continue its trajectory. So you will just restart the process. And the generation of those random variables have to be independent. Okay? From a step to another, they have to be independent. Very important. Okay, some specific cases that are well known in the literature is the case where we have maybe I can clean the board first. Some cases that are very interesting and studied in the literature is the case where we have the death rate that is always 0, which means that you only have birth. Okay? Those type of process are also called fission process because it is like it represents the fission mechanism. Fission, as maybe you know, in the at the level of the atoms, for example. Like when you have the fission mechanism is you have a neutron that have some shocks with atoms and divide those atoms into two parts. So you move from a state where where you had n atoms to a new state where you have n plus 1. Okay. Same with in population dynamics with cell biology. Where in some experiments biologists neglect death rate in biology in the cell population, and then they only assume that you have division. Okay, so the number of individuals in the population will follow a such process where you will only have division and then birth, no death. It is an approximation of the reality, but it is not always true. So, but we do with what we have, and the easiest model that we can get and have the most important amount of information will be the good one. So it is the idea that some have. I will talk about one interesting case. It is the Q model that I mentioned earlier, where you have lambda n, which is assumed to be constant, and mu n, which is assumed to be mu, with an indicator of n larger or equal to 1. This means that we have a constant rate of arrival for the new individual in the queue, and we have a constant rate of removal of the individual in the queue when there are individuals in the queue. Okay, because if we have no one in the queue, we do not have to remove people. So when we have this kind of process, there are a lot of questions that we can ask to ourselves. Is a such process well defined on in the entire time interval, on R plus, for example? Okay, because you can have a blow up at a finite time. It is possible this can be explained by the fact that the birth rate push the population to divide, to give birth to new individuals at a very high speed, so that you have an accumulation of individuals and the population explodes. Okay? So what condition do we have that ensure that this stochastic process is well defined on the total interval of time? This condition is already established. It is a theorem which is quite old, but the oldest reference that I have about it is a book from Anderson. For those between you that are interested in such kind of process, this is a very interesting book. So this theorem states that the BG process does not explode infinite time almost surely, which means with probability 1, because otherwise you can have a positive probability to have explosion. So almost surely if and only if there is the series sum of a quantity which is called Rn goes to infinity, where Rn is 1 over lambda n plus a very awkward term, which is the sum from k to 1, from 1 to n minus 1 of the ratio between the des, the product of des until mu n over lambda k times lambda n. So what is interesting in this term is that we can see that the real problem in the fact that we can have explosion or not is from the first part on the birth rate, because if the birth rate is too large, then we will have this part that will become too small, and like we won't expect this series to go to infinity. Okay? So the idea is that this quantity have to be small enough, the lambda. Okay? And also we have a comparison between death rates and birth rates. Okay, why? Because if lambda are the lambdas are not too large, but they are maybe too large compared to mu, then we can have explosion. Okay? So that's what we have in this expression. I won't discuss about the proof. It is you can go to this book. It is not so easy, but there is a very interesting corollary which states that as soon as we have the lambda n that are dominated by something which is of the form constant plus lambda, constant plus lambda n for all n. As soon as when we have this condition, the birth-death process is well defined everywhere. Birth-death process is well defined on R plus, the domain for the time. So why does it work? Just because of this term, okay? Because if you like you have this quantity that will be larger than the inverse of this one, and the corresponding series will diverge. So we don't have to care about this one. It is this one that is very important for that. And this is quite like it is a very large family of birth rates, which suits well with all the problems we have in biology. So in general, we don't have to look at something larger than this. In some specific cases, but in those cases we have some control, so it is large enough to be helpful in practice. Okay, so I will talk about the long time behavior of this stochastic process. Maybe I can clean what I just wrote. So we were able to say that the stochastic process is well defined on on R plus, then the question we can ask is, what will happen when the time will go to infinity? How do this stochastic process behave? And for that, there is a very important tool that I want to mention. We won't use it so much, but it is something that is very interesting. It is the Kolmogorov forward equation, which is an equation that holds for every Markov processes. So, Kolmogorov forward equation. The idea is the following. I want to describe the state occupation distribution of the stochastic process, which is the probability to localize the stochastic process at each position in its state space. So what I define is U of t that is equal to, as I have here a stochastic process that take values in the set of integers. So I will have U0 of t, U1 of t, U2. So it will be an infinite amount of values where Un of t will be exactly the probability that x of t is equal to n. Is for any n in capital N. So, understanding the long-time behavior of this process is equivalent to understand the long-time behavior of this family, or this infinite-sized vector. Okay? Both are similar. So, but I need to make a precision. It is the long-time behavior of the stochastic process in low, because you can have several behaviors in several senses. Understanding what is happening in low is equivalent to understanding what will happen for those UN. And then we know that those values satisfies, and this is what we call the Kolmogorov forward equation. They satisfy an equation which is the derivative of ut of un. The derivative of un t dt is equal to minus lambda 0 u0 of t plus mu1 u1 of t. This is if n is equal to 0, and if not, then we will have lambda n plus 1 un plus 1 of t minus lambda n plus mu n un of t, and plus mu n minus 1 un minus 1 of t if n is larger or equal to 1. So this can easily be derived from the properties I wrote in the beginning here with the probabilities of having x t plus h equal to n or n plus 1 or n minus 1, knowing that xt is equal to n. It is very easy to obtain this. So it is a bit awkward, but there is a lot of things that can be said here about this process. But something that I also want to mention is a tool that will be useless in this talk, but that is very useful in practice when we are working on those kind of process. It is a matrix which is here transposed, applied to u of t at the position n. It is exact. This quantity corresponds to a certain matrix that can be derived because everything is linear here according to you. So this matrix is what we call the infinitesimal generator of x. In practice, when we have the description of a stochastic process, we are able to properly define this, and the Kolmogorov equation is gun of t is equal to this. Okay? This is what we have in this specific case, but this equality is general, whatever the Markov process you have, and also whatever the dimension. Here we are in infinite, like we are in infinite dimension, because the number of terms that we have here is infinite, but it is countable. You can also like consider cases where you are in infinite and uncountable dimensions, like, and it also works, but you will have operators here. Yes?
Does this result say something about this?
Pardon?
Does this result say something about you? Or,
This, the condition here? No.
Like when does it explode? Like explode in finite time?
If the process explodes in finite time, then you will have a lot of troubles here. Okay? It will be defined. You will always have this. You will always have this, but understand its long-time behavior will be a bit complicated, because when you want to capture, for example, when you have like you take cases where you have extension, where you have some stationary behaviors that emerge. You have conditions that are not that are incompatible with the contrary of this. Okay? So just understand that this one allows you to define the process at any time. Okay? Otherwise, you will define the process properly like this, but up to a finite time. So when I say this, I won't talk about the proof, but it is true. As I told you, this is an approach to understand what is happening for this process in low and in long time. So we use this object which is completely deterministic. We do not have randomness anymore in the expression of this u. And then we have a first result that holds when lambda 0 is positive, which means we have immigration. It is the meaning of this, which means that when the population is at a state where there is 0 individual, we can have birth. This means that we have immigration. So, if this condition holds, then there is existence and uniqueness of a stationary regime P n equal to a limit as t goes to plus infinity of the probability of u n of t, exactly this un, if and only if. So there is existence and uniqueness of this stationary regime if and only if a quantity that I call R1, defined as the sum, another series R1n is finite with what we call R1n is exactly lambda n minus 1, lambda n minus 2, up to lambda 0, over mu n minus 1 up to mu 1. So this means that there is enough death to compensate the births. Okay? So that we can obtain a stationary regime. Because if we have too much birth, the population will explode in long time. So here we have the convergence of this theory if we have enough deaths to compensate the birth that can occur in the population. So and in this case, we are able to characterize this stationary regime. Pn will exactly be equal to like P0 will be equal to 1 over 1 plus this R1. Sorry. And Pn will be equal to R1n over 1 plus R1. So I won't talk about the proof, but the proof is also quite easy. It uses this equation. In fact, what we are doing here is understanding what condition do we have that ensures that the stationary solution of this system exists, is unique and non-trivial. Okay? When you have those three conditions, then you have this limit. It is a property that is linked to Markov processes.
What is the year of this result?
Pardon?
The year of this result.
The year?
Year, yeah.
They are very classical and like if you look any book or paper about, not paper, many book in particular, you will see that. So I don't know the first one that did that. So, but I can tell you, you can like, there are some references that I can give about this. There is Anderson that I talk about that developed this in 1991. There is a very recent, another recent survey from Villemonet and Melea in 2012. But it is, you have a lot of other books on whatever the books on branching, like if you look at branching processes, they will talk about birth-death processes, or books on birth-death processes, and you will see all those results. It is very, yes, it is very classical. Okay, so let's take an example that illustrates this. We consider a birth-death process with immigration, a linear birth-death process with immigration. Linear in the sense that the dependency in n, in lambda and mu are linear. And we add a source term, which is the immigration coefficient, or the 1.2. And we can easily verify that this condition here is equivalent to say that the coefficient of n for lambda is smaller than the coefficient of n for mu. Okay? So in this very simple model, the condition also becomes very simple. So a few computations and you will have this condition. I won't enter into details, but trust me, it works. So this is what we obtain as an approximation of the of the stationary regime for this example, and it looks like a Poisson distribution, but I don't know if it is exactly that. So, a small remark about this result. We see lambda 0 here. So one can say what happens when lambda goes to 0. So when lambda goes to 0, this quantity goes to 0, and this series must converge, and maybe the stationary regime should exist, but no. It doesn't work like this. When lambda is equal to 0, this doesn't work anymore, and there is another result for that. That doesn't use this one, this property, but allow to obtain another result about this. So when lambda is equal to 0, what could happen? We assume that all the birth rates and the death rates are positive for n larger or equal to 1, okay? And the death rate for n equal to 0 is 0. So if we assume that lambda 0 is equal to 0, then the set, the state 0 won't be, like when the population will reach the state 0, it will stay there. It will be an invariant state. Okay? So, and no, there won't be other invariant state. So the population then have the risk to extinct, in fact. Okay, since 0 is an invariant state, we have the risk for the population to reach 0 at a certain moment and stay there. So we will have extension in this case. And otherwise, the population will behave, it will behave and maybe explode. Okay? And the theorem gives some, give a very interesting result that allow to understand what will happen, which means no immigration. So in this case, we will be interested in the extinction probability. So this is a quantity that is very important in my job. For example, what I do every day, I try to understand how some species, like the probability for some species to be maintained in an environment and to be adapted to the constraints in the environment. So I always try to understand what are the extinction probability. And then for this model, the very general form, like not too general, but the general form of this birth-death process that we consider, there is a result that says that we are able to capture this extinction probability. And the result is the following. The BG process almost surely go to, the BG process goes almost surely to extinction if and only if we have the condition, again with some series, the series that I denote R2, which is the sum of R2n goes to infinity, where we have R2n that is equal to mu1 times mu2 up to mu(n) over lambda 1 times lambda 2 up to lambda n. So, and need to complete the result. If the series converges, which means R2 is finite, then the extinction probability from an initial state So it will depend of the initial state. N, I call it N, is given by, so we will have 1 over 1 plus R2, the sum for k going from n to infinity, R2 n. So, R2k. So you will notice here that if you start with a large amount of individual, the extension probability will be small, which is quite intuitive. Okay? The only dependence in n is just here, in the bound of this sum. So here, when we say there is extension almost surely, this means that the probability, the extension probability is 1. Okay, so if this condition holds, then the population will vanish. And if not, then we'll have an extension probability, and otherwise something else will happen, depending on the model. Okay? If you consider, for example, what is called the linear birth-death process, then what will happen will be an explosion exponentially. But with other models, you will have other behaviors. So I won't enter into the detail of the proof, but the idea is to look exactly at the probability for the population to be extinct, starting from a number n of individual, and make just some computation about this using the Markov property. I won't enter into details. An example which is very nice, it is the case of the linear birth-death process. A very simple model for which we will have an explanation on what is the extension probability and when do we have almost sure extinction. Like the linear birth-death process, for which we have lambda n equal to a constant lambda times n, and mu n equal to mu times n. Lambda and mu are positive constant. They are constant. So what we can have in this case is that when lambda, which is the birth rate, is lower than mu, so it is not simply the birth rate, it is the individual birth rate, in fact. It is how we call it. Because you can see this as each individual give birth at rate lambda, but there are n individuals. So the total rate is lambda times n. Okay? Same for the death. So we are saying that, here we are saying that a single individual in the population have more chance to die compared to the chance for him to give birth. So such population will die, in fact, will vanish. So and the inequality is large here. So in this case, the extinction probability is 1. There is a very small difference between the case of an inequality and the equality. When we have the strict inequality, the extinction time, which is the time at which the population completely vanish, it has a finite expectation. Okay? But when we have the equality here, the expectation of this extinction time is infinite. This is the only difference between both cases. And in the second case, when lambda is larger than mu, here each single individual will have more chance to give birth. So you can understand that the population will have, will be, in most cases, exploding. Like the population will explode. But not always. We have a probability extension. The randomness of the stochastic process allows him to extend with a certain probability, which can be small, but not zero. Okay? So in this case, the extension probability it can be, you can compute it using this. It will be mu over lambda to the power n, which is the initial number of individuals. So it is the initial number of individuals. Okay, so that's it. Don't know if we have and I have 5 also. Pardon? Okay. So I just wanted to, I asked for a few time to just mention something. It is something very technical, but I won't enter into technical details. It is what we call scaling limits. I will take a very simple model to show you what it is. Let's consider the so what do we mean by scaling limits? You know, in the nature, the number of individuals in the population are not really like 1, 2, 3, 4. For some populations, like bacteria, for example, you can have a billion number of individuals. Okay? So in those cases, using a birth-death process, it won't be false, but it won't be efficient to use those kind of stochastic processes. Because the simulation, for example, will take so long. So what we do in such cases is assuming that, okay, we have a number of individuals that goes to infinity, and we renormalize the number of individuals in order to get what we call a population density. It is not a population size, or it is not the number of individuals anymore, but it is a population density. Okay? So you can look at it like if we say we have a billion number of individuals, then it is one unit individual, but in the unit of billion of number of individuals. We did a renormalization by by a billion. So this is exactly the idea. So the hypothesis for that, like it is the big tree, I will just say scaling limits. The hypothesis we have are the following. The initial number of individuals, I will parameterize it by k, that you can see as the carrying capacity of the environment with respect to the number of individuals, and so it is something that is aimed to be very large, okay, like the billion, a billion, as I said earlier. So this will be equal to k times x, how do you call it? Partie entière. Integer part, okay. So the integer part of k times x, where x is fixed, it is a positive value. The second hypothesis will be about the rates. We'll assume that the birth rate is also parameterized by k, and we have a decomposition like this, and n. 3, we will have the death rate that will be more or less similar, with the same gamma, very important, plus what we call a competition term, which means when you are in, assume that you are in an environment with some other individuals, and you are competing for the same resource. So when you will have a lot of neighbors, you won't be able to, like you will have a high chance to be killed because they will eat the resource, for example. Okay? So So this is the idea of adding a competition that is a quadratic term with respect to the number of individuals. So it is something like this. So consider this. I will show you some figures, the last figures of the talk, where what we see is that, so I choose the x equal to 1.5. If we assume that this gamma is 0, then we will see in this line that for k equal to 10, we have a stochastic behavior of the birth-death process, which is in red, and we will have the curve in blue is a solution of an ODE. I will tell it. I will tell what it is exactly. And we can see that when k becomes large, the two curves tends to be similar. So here we have a very a significant gap here, but sorry, it is 1,000. We have a significant gap here, but if we increase the value of k, you will see both curves that will be almost they will be superposed. And then we then have the idea to say, okay, like if we have a large number of individuals, we do not have to work with the stochastic process anymore. We just use this ordinary differential equation, which is very simple. Okay? This works when gamma is 0. But when we have a value gamma is, here I choose 1/10. It doesn't work anymore, but the trajectories we have does not explode. They have just a random behavior. So the fact is that there is a stochastic process hidden in this expression. And I will tell what kind of result we have in this case. So the stochastic process that we are looking at will be our old stochastic process over k, renormalized by the number of individuals, by the carrying capacity. So this renormalized stochastic process will converge in a very complicated sense. It is in the space of CAD-lag stochastic processes, like the space of CAD-lag functions, sorry. To a continuous, so this one is CAD-lag, but this one is always continuous, a continuous process. Here, as I said, it is what we call d of 0t. So it is in low in d of 0t r, which is the space of CAD-lag functions from 0t to r. And xt will be the solution of what is called a stochastic differential equation. I don't know if you are familiar with it, but I will write it. So we will have lambda minus mu minus c xt dt plus the square root of gamma xt dbt, where this dbt is a purely random object which is called a Brownian motion. Okay? I think you will have some lectures about this. I'm pretty sure that you will have it. So here, this part is completely random, and this is why it has an impact on the dynamics only when gamma is not equal to 0. When gamma is equal to 0, you have this, which is an ordinary differential equation that corresponds to what is called the Verhulst model, well known in population dynamics. It is also called the logistic growth. This is exactly what you have here. It is a logistic growth, and when you add this part, you have a stochastic term or source of noise in in this equation, and if you assume that C is equal to 0, you have what is called the Feller diffusion, which is also quite studied and well known. So it is a very particular case of result that can be very more general. So it is just to show you that there is a lot of things that can be done, and in order to understand how the population can behave in several scales. Thank you.
Other questions or remarks?
Then I have one.
Yeah.
You mentioned the case of blow up and then the case of stationary state, so the probabilities go to some limit, right?
Mm-hmm.
So can we have other behaviors like, for instance, UN of t is periodic or something like this? Is it possible?
I don't know. I think with periodic, I'm not so sure. But it is true that you can expect a very large amount of different behaviors according to the choice of the parameters. Like if you consider, for example, that lambda 0 is positive, I think you will have either you will have the stationary regime, or I think you will have explosion. Since the randomness won't be, I think it won't be enough to bring back the process from infinity. But it is not like, I think, okay? But when lambda is equal to, when lambda 0 is equal to 0, there are some specific cases for which there is a very exact characterization of what you can get. For example, the simplest model, the linear birth-death process. It is known that when you don't have extinction, in fact, you have an exponential growth, because for the linear case you have this lambda n, and un is UN, and then there is a very classical result on martingales that allow you to obtain the fact that the exponential of lambda minus mu t xt is a positive martingale, so it converges off almost surely to a certain limit, and then your process behaves asymptotically just like this limit exponential, this one, when it is not 0. But with other models, I don't know. And I'm not sure there will be oscillations. In dimension 1, I don't know. I don't know, but I'm not sure.
Other questions? No, if not, let's thank Josué again.
Thank you.